Lecture 1, Introduction to Earth Sciences. Talking about scientific method, nature of science, faith as a Christian in geology. So the nature of science is best described as a search for truth through repeated experimentation and observation to better understand the world. We do this every day, all the time, without knowing it. It's part of us as humans. God has created us to have this innate curiosity, which should be fostered and developed in a logical and reasoning way. The nature of science says that we have these tools, okay? And on this slide, we have a bunch of listed tools. You have terms like qualitative, quantitative, qualitative being, the quality of something, a description, picture, things like colors, soft, hard, bigger, better, those types of things, right? Qualitative observations give us secondary understanding of a phenomenon. Quantitative observations are much more usable in a hard science. That it has numbers associated with it. And so while I could say, a water sample has a very acidic quality to it, I could actually assign a quantitative number, and I could say, the acid is a pH of 3.5. And that would provide a much more concrete observation versus a qualitative observation. You could say, the water feels slippery, which is often associated with a basic water. But quantitatively, the base would be a higher number. So maybe, a pH of 12 or 13. Okay. God has given us a very broad sense of the world. We can taste, touch, feel, hear, all these different senses. And, why would God give us so many different methods of observing his creation if he didn't want us to observe it and study it? And so I think the nature of science is really all about understanding God's creation. And I don't think the two are in contradiction of each other. A lot of people say, I'm a religious person, I don't believe in science. Or, I'm a scientific person, I'm an atheist, I can't believe in God. And I think as Christians, our worldview needs to be blended. We can study hard sciences and still have a deep religious understanding. And so that's kind of what we're going to try and do throughout this course. We're going to utilize technology. We're going to collaborate with peers. We're going to use a common process during our investigations. We're going to look at models. We're going to get into different types of data and collecting qualitative and quantitative observations. And we're going to use this thing called the scientific method. Most science classes start with the scientific method. And there's a lot of different scientific methods out there. Essentially, we have a problem, we come up with an idea, we make some predictions about the idea, then we test it, and then we collect data on whether or not our predictions were correct, and we adjust as we need, and it's more of a cyclical process, ultimately to try to solve society's problems. Go ahead and pause the video, and in the PowerPoint, you'll find this link. Go ahead and watch that video, and then come back to the PowerPoint when you're done. Okay, so here is the scientific method steps that we're going to be using in this class. And you're going to get a chance to practice this in the assignment here at the end. When doing science, you need to understand that science has limits. You really need to be careful about this. Charles Kettering says, beware of logic, because logic is an organized way of going wrong with confidence. I love this statement. It applies to so many different things that can be hot button topics in our society. Things like vaccines and COVID and, all pharmaceutical companies, and there are all kinds of stuff out there, right? You need to be aware of the limits of science. There are sample size problems, there's logic, biases, different control variables, looking at qualitative data versus quantitative data, and so on and so Understanding the nature and limits of these will help us utilize models more appropriately and bring some erroneous results of science kind of back under control. We are going to need to use models in Earth's history. So specific to geology, the Earth is really big, it's really complex, it has a long past history, whether you're talking about millions of years or thousands of years. We don't have the ability to go back in time and see what the Earth looked like when it was first created. I'm going to put a pin in this discussion until we talk about the age of the Earth, but whether the Earth is millions of years old or whether the Earth is 6,000 years old, we can't go back in time and look at it. And so from a atheistic view or from a religious viewpoint, Earth's history is a small, limited bubble. We have small sample sizes of a very large, complex, and old thing. And so there are a lot of challenges with Earth's history. I love this. I took this figure. You're going to read about this in the discussion board this week. It's a great diagram. You have this big square in the background. Everything in the universe is composed of things that are true and things that are false. All right, we can have theories, and some of those theories are going to be true, and some of those theories are going to be false. And if you come up with a theory of everything in the universe, you're going to fall into either true or false. Within that bubble, you have science. Now, science can help us prove things that are true, and it can help disprove some things that are false. But there's no way science can touch all things in creation. And so you have to understand that science will provide us very good information over a limited scope of the universe, the full creation, or however you want to term that. And so I think going into this, you have to have some white space. The white space is stuff that goes beyond science. There are things in our universe that are above and beyond our ability to know. And for those types of things, we have to lean on theology. And so theology can help us explain things that are false and things that are true, which science cannot touch. I love this diagram. It's a great diagram. Highly encourage you to read through chapter 1 and 2 of the Brand and Chadwick's PDF that I asked you to download. Really good stuff in here, and it really helps us pull science into perspective from a Christian worldview. So we use theories to make advances, and a good theory needs to be adjusted and replaced when new evidence presents itself. So good theories are organized, they explain previous facts, they suggest new experiments, and they can be falsifiable. They predict outcomes of experiments or data not yet conducted. Einstein has produced a lot of really good theories about things that he couldn't prove, or he couldn't even do experiments about, but the things that he put into place after his time has come, the current evidence is supporting stuff that he had thought about. And that's what makes a good theory. There's a couple different theories here. This is the ruling theory hypothesis. This minimizes change and divergent thought. It explains past evidence really well, but it does not leave room for new stuff. Evolution is a good example of the ruling theory's hypothesis. It does a really good job explaining how things came to be, but when we get new information such as genetic data, new fossil evidence, new soft body fossils, that sort of thing, the ruling theory hypothesis doesn't allow for evolution to change. And so this is a big problem with the evolutionary theory, is that it's not adaptable. You have a single working hypothesis. This is a different way to look at theories. It allows for new data to adjust and move forward. So, for example, gravity. Gravity, once upon a time, I think it was Archimedes said, when you throw a rock up in the air, it wants to come back to Earth because that's where the rock lives. That's its home. Water. When water is evaporated out of the ocean, it falls on the mountains, it runs down the rivers, and eventually it goes back to the ocean. And gravity was thought that things were just trying to get back to where they belong. And then, that since has evolved into having a mathematical formula and a gravitational constant. And, Sir Isaac Newton comes up with this beautiful, elegant equation to describe gravity, and gravity is the same all over the planet. And then, Einstein comes along and puts a different spin on gravity and say, well, maybe gravity isn't exactly that. Maybe it's not mass being attracted to mass, but maybe it's the deformity of space-time fabric, which is causing things to fall down these gravity wells. And you could say the same thing for atomic theory and the theory of plate tectonics. These are really good big theories that have continued to adjust and adapt over time. I like this one, the multiple working hypothesis, and I think this represents that diagram of everything in the universe being true or false, and how science can only address some of it. This was originally coined by Thomas Chamberlain, who was a very well-known geologist in the late 1800s. He allows the possibility that we could have it wrong, and we might need to completely scrap our current understanding and develop a completely new idea. Dark matter is a great example of this. Dark matter is trying to explain a problem with the gravitational theories that we currently have. We have galaxies that are not rotating like they're supposed to. And we have this mathematical error. And so you have a couple options. Either one, our understanding of gravity is wrong, or two, there is this thing out there that we can't detect that must be affecting the gravitational equation. And for lack of a better term, we call it dark. So dark matter is messing this up. Or, we don't have a good understanding of gravity at all, and we need to scrap the whole thing and start from scratch. Maybe it has nothing to do with math or dark matter or any of that. Maybe it's something completely different. And this allows for supernatural influence. Maybe God is causing these things that we don't really understand. And so this supernatural, or this idea of things outside of the realm of science might be true. And so that's a multiple working hypothesis. So there are different ways to look at theories and data and evidence. So what I'd like you to do, go and pause the video and watch this video. It describes a practical working relationship between science and religion. And it gives you a couple different options. So I'll pause here for a second, watch that video, and then come back. Okay. Now, one thing that we need to really hold on to as geologists, as Christian geologists, is that God is going to be the standard. Now, if science brings forth evidence that at first might go against what God is teaching, that's okay. You're going to have faith that eventually science will point towards God. You can have misconceptions. You can have a small set of data that might at first go against the teachings of God, but we have to have the faith that our God is the standard, and then with more research, with more science, we might find out that at first the data that might be counter God is actually pro God. And so having this confidence in what we hope for, and having the assurance about what we do not see, that missing data, it really is important to kind of keep that at the front of our mind. So we're going to skip through a little bit of this. This is the Age of Enlightenment. There was a shift in thought. we were not all secular atheists. We were very Christian-oriented, God-fearing monks, which were trying to understand the world around us. And then somewhere along the line of this age of enlightenment, where we really relied on data, we shift where our authority was and what our standard was. We started to become smart, and we started to rely on ourselves, and we moved from God as being the standard and the Bible being the authority to, humans are the standard. It's a very humanistic viewpoint where we know what's going on and we have a better understanding than God does, and we forget about God and we rely on ourselves. And when you do that, we have to draw our authority from something. And so if we're going to rely on ourselves, we want to rely on our processes and our scientific method. And so there was this shift away from a biblical authority and God as a standard towards a scientific method as authority, and humanism or human intellect as our standard. And so this is kind of what was happening during the Age of Enlightenment. Here's a couple biblical anchor points that we want to hold to. I'll let you read through those. We have a relationship between Bible and science. Just kind of a little chart here. Okay, back to the text, chapter 1 and 2, talking about limits of science. These relationships between science and the Bible, if you read through these 5 different options, the 2 that are probably the most healthy relationships between Bible and science are number 3 and number 4. Number 3 recognizes that there is authority in the Bible and in science, and both can be relied upon. And you need to understand that the Bible speaks to some things and then does not really speak to other things. And you can read between the lines and you can try to make the Bible talk about dinosaurs. There's mention of great lizards and stuff like that. But that's not really the purpose of the Bible. And so to use the Bible as an authority figure on dinosaurs is a little bit of a misuse. Whereas if you look at the science and the fossils about dinosaurs, that's going to be a little bit more reliable when it comes to dinosaurs. Now, when it comes to other things, conflict will always arise. And a lot of this is because of our limitations, because of the purpose of the Bible, and how things have changed in our natural world. So I like number 4 here. If you have a conflict between the 2, then, if the Bible is speaking on the topic, and it is in direct contradiction to the science, then we grant the Bible a higher level of authority. If the Bible and science are potentially in conflict, but the Bible doesn't really talk towards it or doesn't speak towards it, and the science doesn't really negate anything in the Bible, you can rely on your science. So this critical thinking between step 3, option 3 and 4 here, I think is a good, comfortable place to be, and you can wrestle through different issues. We want to avoid this. Religion is for things of the heart, and science is things that are objective. This is kind of a skewed bend. We want to really avoid this. It puts religion in the back seat and removes scientific credibility from the Bible. The Bible definitely has some scientific credibility. There are things in the Bible, you can even think about, germs and the washing of hands. The Bible knew about germs. God knew about germs, knew that cleanliness was an important thing. And you don't need a microscope and, the study of germ warfare to figure out that the Bible is speaking truth in this respect. And so, we want to avoid the feel good, well, I really feel that this is what God wants me to do. That's kind of whimsical. Our heart is something that will go in the wrong direction very often, and so I think more of commitment and reliability in religion, not just science. So just be careful here. It's an easy way to go awry. This is a good flow chart to kind of help us relate the two. You have a science domain, which goes through scientific testing. This cycle over here, hypothesis, and the development of it, the testing of it through observations, experiments, analysis. That is a scientific process, the scientific method. It interacts with the Bible or interacts with religion. When conflicts arise and the Bible speaks to it. So if you think there's an issue between science and religion, it's always a good idea to dig into the Bible. What does the Bible say about this? If the Bible doesn't really speak to it, then you're good to go. Move on. The science is good. Keep moving. If the Bible directly contradicts what the science is saying, maybe we are at a very superficial introductory level of the science, and we have to have confidence that at some point the science will eventually come in alignment with the Bible. And so this can be good to question what's going on. You can treat science as a phenomenon, and then you look into the Bible to see what the Bible says about that phenomenon, and you can go back to your science. And the interaction between this tension will help you become more godly, and it will help you produce better science. So here's my ending remarks on this. We don't need to fear data and honest research. We can do hard secular science. We predict that since the Christian worldview is based on truth, careful scientific study will actually expose a higher level of understanding in terms of biblical origins and our Christian worldview and our theology. God is invested in humanity and has been known to intervene supernaturally. So understanding that science cannot answer every single question in the entire universe. It has a small domain compared to all the other things that are true and not true in the world. And God has the ability to step in, the turning water to wine, right? Turning fruit and water and yeast into wine is a naturally occurring process that is scientifically proven, and it takes many, many months to make good wine, to let that ferment over time. God can intervene and speed up that process and supernaturally make wine in a matter of seconds. And so if we find the Bible to be true and authoritative, then we know that that story is true and authoritative, and God has supernaturally gone beyond a natural, slow process. And so we need to allow for that. It doesn't mean that you still can't make wine over the course of 3-4 months. It's just in that instance, God stepped in and intervened. So special actions had to be taken to deal with a sinful and evil world. And so you have the geological story of the Grand Canyon and plate tectonics and continental drift. And you can apply this idea of natural, long-term, slow geologic processes. These are measurable. There's a lot of scientific evidence to support it. But God has been known to intervene supernaturally in the past, and this could have been an example of when he intervened supernaturally and sped this all up because of our sinful and evil world, creating the global flood. And so that is responsible for a lot of our geological formations, which can also be explained through slow, natural geologic processes. So there's a tension here that we want to try and balance. So understanding that God is fully capable of taking special intervening actions, understanding that Christians don't need to fear data because eventually the data will end up supporting God and the Bible. These are all things to just kind of keep in the front of our mind as we go into what is traditionally a very secular and difficult concept. So what we're going to do, we're going to go into the scientific method notes handout. There's more in the lecture here, but I think it's going to be better for us to just jump right into expectations for your project. Okay, so when you go through the scientific method process, you're going to hit all of these components here. We've got them kind of numbered. You make an observation, you're going to write a testable question, design an experiment, come up with a prediction, collect your data, analyze your data, and then draw some kind of conclusion. And so you're going to go to a website and kind of click around and play around. You're going to find an experiment that, one, you understand, and two, you can collect quantitative data, quantitative observations. All right, play around with one of those simulations and find one that meets those criteria, and then come up with a testable question that this simulation can answer. A testable question is going to be a question about your observation, and it specifically includes an independent variable and a dependent variable. So to review an independent variable, it's the thing you're changing, the thing you are manipulating, the button or the slide rule that you're manipulating in your simulation. And then the dependent variable is the measurement that results from you changing the thing. And so I'm using the example down here. Do some species of tree grow wider than others? Or a different way to phrase that is, what's the relationship between the tree width and tree species? And so my independent variable, the thing I'm choosing to look at, is species of tree, and I am measuring tree width. I could measure all kinds of different things, but this is what I'm kind of landing on. So you're going to need to come up with your own testable question that includes the independent and dependent variable. Then you're going to design your experiment. I've given you a table so that you can clearly lay out your independent, dependent variable, your control variables, those are the things that you're not changing, and possible areas of error. I'd like you to take a screenshot of your simulation, and you're going to paste that next to it. You're going to put this all together in a nice, neat little package. You're going to come up with a prediction. Your prediction or your hypothesis should be in 3 parts. I need to update this handout. Sorry, it's a little bit off. If, then, and because. So you got 3 pieces. And so you want to be specific and you want to be vulnerable. Okay. Now, after you kind of click around and you play with your experiment, your hypothesis very easily could be correct, and that's fine. We're kind of going through the motions to get used to you working with the scientific method here. So here's a sample hypothesis. It says, if different species of tree are measured, then slow growth trees like oak and beech will be smaller in diameter because, and this is where I forgot to add, because they don't grow in wet areas. Okay, and so I have an independent variable, a dependent variable that's specific. I kind of picked which ones I wanted to do. I could have changed it. I could say, if different tree species were measured for diameter, then oak trees would be widest because they grow to be older, right? Period. Or whatever, right? So have a vulnerable, specific prediction. If, then, because, include a specific independent, a specific dependent, and a specific reason. All right. You're going to have to make a table. You could do this in Google Sheets. And I listed my independent variables. Now I have pre-picked which trees I'm going to look at. and then my dependent variable, very specific, with units, and I have at least 3 trials. So I'm going to find 3 different trees of oak, 3 different beech, 3 different maple, 3 different sycamore. And I'm going to take the average. Right? This is what you need to collect from your simulation. Now, because we're using a computer simulation, it might not make sense for you to have 3 trials, and that's okay, because it's a computer. You put in X, you get out Y, right? Then you're going to do your data analysis. You're going to graph this information. So you're going to graph tree species, and I'm going to graph the average diameter of the tree in centimeters. I want to put my independent variable, that's tree species, along the x-axis, and I want to put my dependent variable, which is the diameter of the tree, along my y-axis. Now, if I'm going to make a bar graph, I need to understand, in order to decide whether I need a bar graph or a line graph, I need to look at my data. You think about how many data sets are between oak and beech. There aren't anything. There's nothing between oak and beech. Oak is its own thing, beech is its own thing, maple is its own thing. These are discrete data sets. They're groups, and so I'm comparing these groups. And so I have discrete data, and I'm going to use a bar graph. If I had something in here like time, pretend like I had 1 hour, 2 hour, 3 hour, and 4 hour. Well, how many data points are between 1 hour and 2 hour? Well, there's an infinite number of data points between 1 hour and 2 hour, and so I have continuous data. Continuous data needs to be graphed like a line. So depending on what kind of data you're collecting, you're going to decide if you have a bar graph or a line graph, independent variable on the x, dependent variable on the y. Once you're done collecting your data, you analyze your data, you figure out what you learned, you're going to write a conclusion in a claim, evidence, and reasoning form. So your claim, you're going to go back to your original question, you're going to answer your question, right? Which tree was bigger, right? You're going to support it with data. So refer to your values, refer to your trend line. I found that maple trees were almost twice as much, to two to three times as wide as oak and beech trees, right? And then provide some reasoning as to why that is. And you might have to do some additional research. You might have to do a quick little Google or ChatGPT. Why are maple trees wider than oak and beech trees? And see what you come up with, right? Try to provide some scientific reasoning for the data that you got. Okay. So what I'm going to do, I'm going to break from here, and I'm going to open up the PhET lab, and I'm going to look at the assignment. I'm going to go walk through that for you. Okay, here is the experimental design activity. The purpose is to utilize the scientific method that I just reviewed to develop a claim about the world, and you're going to present it in an organized, professional manner. It's a one-page lab report, a little summary of what you did. So the design is you're going to use a computer simulation to run an experiment of your choice, and you'll need to follow all the aspects of the scientific method. Keep in mind the nature of science, important skills that go into doing science. Those are all in the PowerPoint. If you are unfamiliar with some of those, feel free to review them. I did kind of skip over them. We'll review them as we need to coming up. So the first thing you're going to do is go to the PhET simulations, and you're going to pick a simulation that you understand, you can manipulate the independent variable, and you can collect quantitative number data. And then you're going to use this Google template to put it all together, and you should be able to submit to this assignment itself. So let's see what this looks like. So there's a whole bunch of different things in here. There's a couple that you should not do, like the density one, the buoyancy one. Just leave that alone. If you come over here and you click on physics and earth and space science, usually that will help narrow down some things. There's a bunch of different ones that you can do. The skateboarding one is good. The gravity one is good. There's some forces in here. Coulomb's law, masses and springs are good. The projectile motion is good. Find one that you understand. I'm going to use the projectile motion one. I'm going to click on the play button, and I'm going to do the lab. I think it gives us the most options here. Start out by clicking just buttons to see what I have, and I can change this launch speed. I can change the height of the launch, the angle of the launch. I can change what I'm shooting, or I can change the mass. I can add air resistance. I do all kinds of these different things. I'm going to keep it with a cannonball, and I am going to choose to control the height. I'm going to have 0 as my launching height. I'm going to have the initial speed, launch speed. I'm going to keep that the same. And what I'm going to do is I'm going to change the angle, and I'm going to measure the distance. Okay, so I'm designing my experiment. My independent variable is going to be the angle, and I'm going to change the angle every 10 degrees. So I'll do 90, 80, 70, 60, 50, 40, 30, 20, and it looks like I can't go down to 20, so I'll stop at 30. So I'll go from 90 to 30. I'm changing my angle at even increments, and then I'm going to measure the distance. So independent variable is launch angle, and then dependent variable is going to be distance. So the way this thing works is you can drag out this little plus. So you put the little plus button where I'm going to launch. It's kind of hard to see right there. And then I'm going to measure to where I go, and it will give me my units of meters. It'll give me my distance in meters. All right, so that's kind of what I'm going to do. I'm going to take a screenshot of this so that I have a sketch that I can put in. I'm going to come back to step 2, and I'm going to choose this Google template. Hopefully this works for you guys. If I can go to it, it's going to make me make a copy. You're not going to have group members because we're individual. What I'm going to have you do is just put your last name and just go ahead and put down PhET Lab. So here's the template. Right up top, you're going to replace my words with your words. So the testable question needs to have an independent dependent variable. And so looking at the launch angle and the distance, I might wonder, how does launch angle affect the distance a cannonball go? The distance a cannonball goes. All right, so that's my testable question. Snapshot of the experiment. I will take a snapshot and paste it in here. My variables, my independent variable is going to be the angle of launch, and that's going to be in degrees. My dependent variable is going to go the distance, and it's going to be in meters. Things that I can control, right? Air resistance, the launch height, the launch speed. What else was there? The weight of the ball, the diameter of the ball, gravity. So all these other things that I'm not changing, those all become control variables. Okay. So you fill that in, you finish that out. Your hypothesis is going to be in the if, then, because. So if a cannonball is launched at the highest angle, it will go the farthest because it will be in the air the longest. Right? That's my hypothesis. Now, I could be wrong. I could be incorrect. if a cannonball is launched at the highest angle, then it will go the farthest. And my reasoning for this would be because it's in the air longest. Now, I don't know whether or not that's going to be correct or incorrect. And so what I'm going to do is I'm going to collect some data. Now, there's a couple ways to do this. You can insert a data table here. Okay. So I've got something like this. You can manipulate how this is wrapped. It's right here. There it goes. Formatting options. So you can kind of play with this to try and get it to, there we go, look nice and neat. You can pull this information from Excel. Or you could pull this from a Word document. Or whatever it is that you need to do, right? So I'm going to preload this with my measurements. Insert row, right, etc. For all the angles that I'm going to do. And then once I start launching, I will collect my data, right? And I'll start filling that in. And then I'm going to graph this data. You can do that in Excel, like I said. And then you're going to have a little conclusion about why you think this is happening. Okay. I'd like this all to be on one page. So you try and manipulate this so it's a nice single page snapshot of your experiment. And then you're going to go ahead and post that to the experimental design activity.